Okay, so now we're going to talk about the trapezoidal rule. And you can think of the trapezoidal rule, of course, as arising from the fundamental theorem of calculus. So if you recall the fundamental theorem of calculus, then what, of course, it says is that the solution at a given time is equal to the solution at a reference time plus the integral of the vector field along a solution curve from the reference time t0 to the current time. So let's think of this in terms of a dummy variable tau instead. Okay, and of course what you can do then is that you can approximate the integral by some sort of quadrature rule. And in particular, if you use the trapezoidal rule, then what you get is that this is approximately y at t0 plus t minus t0 over 2 evaluated at the vector field. It's like at both the left and right endpoints, which would be y at t0 plus f evaluated at y at t. Okay. All right. So if you then think of this as a numerical method, it's like where you sample the trajectory at a bunch of points, then what you get is the following method. So this leads to the trapezoidal rule. For ODEs, which has the form that y at the new time, y at n plus 1 is equal to y at n plus h over 2, f evaluated at yn tn plus f evaluated at yn plus 1 tn plus 1. Okay, all right, so that's what we call the trapezoidal rule. So you can ask, as before, it's like what the order of accuracy of this method is. Okay, so what you do, it's like in order to determine the order of accuracy is that you need to essentially substitute the exact solution into the equation which defines the numerical method, and then you want to look at the error, it's like when you do that. Okay, and so this is going to give you some indication of the what is called the truncation error. And you might ask, well, how do you actually go about substituting the exact solution here? And the way you do this, of course, is that you replace these solutions by their corresponding Taylor expansions. Okay, so what you do is that you substitute y at tn plus 1, okay, as a proxy for y sub n plus 1 is equal to y at tn plus h over 2. So f evaluated at yn tn, okay. Okay, so this is going to be y again at tn, tn plus f evaluated at y at tn plus 1. Okay, so I've not really done anything except that I've replaced this numerical sequence of solutions with their corresponding exact solution flows. Okay, and then once you've done that, now you have an expression. Actually, I should say I am subtracting this off. Okay, so I'm subtracting off this whole thing here. Okay, so I want to see the extent to which this equation holds true if I replace the the numerical sequence of solutions, it's like with the exact solution flow. Okay, all right. So what you do is that you imagine Taylor expanding the exact solution now about some reference time. It's quite natural here to expand about time Tn. Okay, so I'm going to replace this y at Tn plus 1 by its corresponding Taylor expansion. So this is going to be y at Tn plus h times y prime at Tn, right? Plus 1/2 h squared y double prime at Tn, plus something which is big O of h cubed. Okay, so this is just the Taylor expansion for y at Tn plus 1. And then I'm going to do something similar here for this term. It's like which involves evaluating the vector field. It's like at y Tn plus 1 as well. Okay, so this is minus y Tn plus 1/2 h of f at y at Tn, which is of course y prime at Tn. Okay, and then this is second term is, so we're going to do essentially again a Taylor expansion of this. So this is going to be y prime at Tn as the leading order term, plus h y double prime at Tn, okay, plus something which is big O of h squared. Okay, so you might ask, it's like, why is it that we expanded this Taylor expansion? It's like for y at Tn plus 1 to big O of h cubed here, but you only expanded, it's like this term here to big O of h squared. And of course, that's because this big O h squared term is being multiplied with a factor in front, it's like of h. And so, so at the end of the day, it's like you're expanding both of these terms to big O of h cubed, okay? All right, I mean, so let me rephrase that the error terms, it's like what you have, it's like in both instances, at the end they are big O of h cubed. Okay, so you can check that when you subtract off these things, this term will cancel with this term. There's this h y prime at Tn term, and I'm subtracting off a h over 2 y prime at Tn plus y prime at Tn, so this term will cancel out these two terms. Right, and then you have a 1/2 h squared y double prime at Tn, and then it's again a 1/2 h squared y double prime at Tn term, so this term cancels out this term, and then you're left with something again which is now big O of h cubed. So what you see is that the residual error, the extent to which the exact solution satisfies the defining equation for the numerical solution, right, has a residual error of big O of h cubed. Okay, so this is telling you something about the truncation error. So this is the local truncation error. All right, and so you always know that this has the form of big O of h to the p plus 1, where p is the order of the method. So this is telling you that the order of method is 2. Okay, so this implies that the trapezoidal rule is second order. Okay. All right. So so this is all you're really doing right now is you're doing a local error analysis. So the next step of this is to then prove that you actually have global convergence. So that's the next thing which we'll discuss. Okay.